Good to have Evgenii Vladimirov. This is another of our Center for Econometrics and Business Analytics seminar. And Anton asked me to host you, Evgenii. So welcome, everyone. Good to have Evgenii, who's doing some very promising, very nice work. Evgenii is at University of Amsterdam. And I understand that he's a PhD candidate there, right?
Yes.
All right. Well, we usually have an hour, and if that's okay, we will interrupt. If not, we'll keep our questions till the end. Up to you.
Yes, you can ask whenever you want.
All right. Thanks. And then take it away.
Okay. Thank you very much. Thank you for the invitation and for giving this opportunity to present here. I'm very happy to present at CEBA. I wish we had this center when I was studying at St. Petersburg. Yes, but now I'm a PhD student indeed at the University of Amsterdam, and I'll be presenting my joint work with my supervisors, Peter Boswijk and Roger Lavin. So I'll be talking about estimating option pricing models using a characteristic function-based linear state space representation. So yeah, I hope you can hear me well and see my slides. So yes, as you can see from the title, I'll be mostly, I will be talking about the option prices. And let me start with motivation, why we're interested in option prices and how are they useful for us, and to make some inference about the stock price dynamics. So let's say we are at time small t, and we know that the price at this time is st, and in the future there will be just one realization of the past of this of stock prices that will essentially occur throughout the time. But when we are time small t, we actually do not know which one of these realization will happen. So that's why we're thinking that there is a continuum of possible realization of possible paths that might happen from time small t to capital T. Okay, and so all of them, they some sort of form a distribution at time capital T of the values of this asset ST. Okay, now we might say, for instance, we want to hedge or buy protection against the downward movement of the stock price ST. So let's say we want to buy a contract that would pay us K minus ST if the price falls at time capital T falls below this level K. Okay, so that's in some sense that's an insurance of these downward movements. And of course, the natural question would be, what is the value of this type of contract? And this is the so-called plain vanilla put option here in this example. And as you can see, these types of contracts will be, in some sense, a function of the distribution that of the potential stock price, of the value of stock price at time capital T. Okay, but in order to value this contract, what we also will have to take into account that there is also a risk aversion of investors. Therefore, this price of this contract will depend not only on the probability CDF function of physical density of this stock price at time capital T, but on the so-called risk neutral density Q. So the risk neutral density Q is essentially the physical density weighted by the subjective risk aversion parameters of the investors. So, and of course they're interlinked to each other. But still the price of this contract will depend on some sort of the density on this risk neutral density, and it means that it will also depend on the dynamics of this asset from time ST to time capital T. By the way, can you see the bottom part of my slide here? Okay. So yes, and that is essentially the idea that, so if we know the dynamics of the asset prices as T, then we can find the values of the option contracts of these option prices. But that's also goes the other way around. So if we know the option prices, we observe them in the market, then it means that we can make an inference about the dynamics of the assets. So you see that we can make an inference not only about the whole distribution of this asset ST. And of course, in the literature, there's been proposed many parametric option pricing models, starting from Black and Scholl's models. And in this paper, so we are trying to answer the question, how can we estimate a parametric option pricing model and filter out some latent states with low computational costs and exploiting all available probabilistic information from option prices. Okay, I see the chat. Okay. What is psi? So psi here is the so-called state price density. So that's related basically to the risk aversion parameters of the investors. So there are different ways to model that, and I think one of the ways to assume some utility functions for investors, and based on that you can also derive this price density, but there are also different approaches. But in this paper we'll be focusing only on this risk neutral density, risk neutral dynamics. So what is on the left side here. Okay, to give you an example, to motivate again a little bit more on this question, let's consider this small example. This is a prominent, very famous Heston model, widely used by practitioners and also academics. So the idea is here that, unlike in the geometric Brownian motion, like under the Black-Scholes assumptions, the volatility here is allowed to be stochastic. So it follows square root process, so with mean reversion and some diffusive part. So, and it has in total 4 parameters, but the volatility process is latent as well. So in a Black-Scholes model, for instance, you have only 1 parameter sigma, but here we have 4 parameters and also the volatility is latent as well. So if you want to find these parameters, to estimate them, one of the most naive approach that is taken in the literature is called calibration approach. And the idea is that let's just minimize the square difference between market observed option prices, the one that market trades, and the model-implied option prices. Okay, we minimize it for all available options at day T and throughout several days if we have so many days or years. And yeah, so of course these model-implied option prices they are highly nonlinear functions, highly non-trivial functions, and in practice we need to use some Fourier-based methods or simulation-based methods to find the value of these prices conditional on the parametric, on this Heston type of parametric model. Okay, and as you can see, this is a function of the parameters. It means that if we start iterating, estimating these parameters, for every iteration, we'll have to re-find kind of these model-implied option prices. So that adds up to computational costs. But what is more important here is that the volatility is actually also latent. It means that we will treat it as an additional parameters for this optimization procedure. So in total, we will have T plus 4 parameters to calibrate, and that essentially lead to huge computational costs, especially if you use data over 2 years, several years, let's say. So okay, yes. I should be more probably specific. KI is the strike price of options. So we assume that here at day T we have several options with different strike prices KI. So in my drawing here, I used one strike price K, but here I say we have several strikes at a particular day. Yes, and for each option with different strike price, we will need to find model-implied option prices. And but another problem here with calibration in general that it doesn't take any time dependency into account. So it ignores completely that the volatility has some time dependent structure. So you can easily calibrate this model for different days. So conditional, like using some constraint that the parameters are the same for different days. So all in all, this leads to highly computational intensive procedure, and in the optimal filtering of volatility, of the latent volatility process is not optimal in the sense that we're not capturing the time dependence of the volatility process in this case. Okay, of course, there are many different approaches proposed in the literature for the estimation. There's some so-called calibration-based methods or that use nonlinear, penalized nonlinear least squares, efficient method of moments, implied state methods, some Bayesian techniques, particle filtering, and but most of them still use, for instance, the option prices as inputs for the estimation procedure, as it is here, for instance, or the monotonic transformation. For instance, people often use Black-Scholes implied volatility as inputs for the estimation procedure. But if you do that, it means that you still will need to price option price conditional given the parametric specification. So you will always need to find this model implied option prices. Okay, and you need to use some Fourier or simulation-based methods. Again, as I said, that leads to high computational costs. And there are two exceptions that I'm familiar with that actually do not do that. And our paper will be very much, in some sense, related to this first paper by Feanor and Oku. And so, but all these computational costs most of these estimation approaches lead to people say, okay, let's just use, for instance, few options per day. Very often people say we will be using only at the money options, just one option per day. Or they say, let's use weekly options. So for instance, Wednesday options and ignore the other days. Of course, that reduces computational costs, but that is not optimal because we're just simply ignoring part of the information. So in this paper, what we propose is a new estimation procedure that allows us, that basically doesn't require any numerical option pricing techniques, option pricing methods, but at the same time, it exploits the time series structure of the model. So if we assume volatility process with square root process, we take into account this time dependency structure. And it is based on the simple Kalman filtering technique, which makes it very computationally fast. And at the same time, it also exploits all probabilistic information via the characteristic function. Okay. Whoops. Yes. Okay, so that is, yeah, that source of motivation, but let me again draw your attention to some information on option prices and what can we extract here a bit with some more details. So let's say again, we have put options with strike prices K, and there's a time to maturity tau. The payoff of this function of this put option is K minus ST, and if it's positive and zero otherwise. So the price at time t small t is essentially a risk neutral expectation of this payoff function, which we can write it down as an integral with respect to this risk neutral density Q that I that I showed you in my drawings at the beginning. So so yeah, it means that if we take the derivative of this put price with respect to the strike, then what we will get is essentially the risk neutral CDF of this stock price ST at time capital T. And if we take the second derivative, then we will get the so-called risk neutral density. So we will get this relation where we see that the second derivative of put options with respect to price, strike price, is related to this risk neutral density Q. Okay, and this is of interest per se from many people. This is, for instance, an example from the ECB economic bulletin of this risk neutral density extracted from Eurostoxx 15 options. And you see that for 3 different days, and this is, for instance, 21st February with blue, that's just a week before the outbreak of coronavirus in Europe, and just a week after, 28th February, when the outbreak occurred, and you see that this risk neutral density becomes much flatter and with much fatter tails on the left side here. And on 20th March, after some announcement of economic stimulus in Europe and in the US, you see some shift to the right side, but the tails are still fat here. So, but this is just an example of this risk neutral density.
Evgenii, may I ask a question?
Yes.
Is it possible to say something about the degree of heavy tailedness, that is, the tail indices of these distributions? I understand that the blue line is the most heavy-tailed one. I wonder if the variance is finite in particular, and the first moment should be finite, definitely, I suppose, because then we will take expectations with respect to these densities. But how is it seen from the tail indices?
So this is just an illustration here, but in general, yes, you can. I think you can. There are some papers by Victor Todorov and Torben Andersen who look at the tail risk measures using the option prices, and they trying to extract basically the information about the heavy tailedness of this risk neutral density at a particular day, and they analyze the dynamics of these indices.
But who is the second author of the paper, Todorov and whom?
Torben Andersen, I think.
Andersen, thank you very much.
They are both from the Northwestern University. So yes, but let me continue here. So if we extract, again, as I said, this risk neutral density Q can be extracted from the prices, put and call option prices as the second derivatives with respect to strike prices. But it means that if we take any other payoff functions, J, like general payoff function, so in our example before, that was a max minus KST for put options, but it doesn't have to be the max function, it can be any other functions. And then if we will decide to price some derivative with this payoff function J, then the price of this will be also this conditional risk neutral expectation with the same risk neutral density Q, but now we can plug in here this the second derivatives of these put and call options, and we split this integral into 2 for convenience to use put and calls. And if we apply integration by parts here twice, then what will end up that the price of this general payoff function, general contract, it can be written here as position in the bond and some integrals with respect to basically with the second derivative of J and put and call prices here, which I denote by always just for out of the money options. What is CKXT? Yeah, so I have I have put options and I have call options. So with CK, I denote the second derivative as here, but for the call options, and call options are options with payoff function st minus k. But here for put k minus st. Yeah, so, and the idea is here that if we want to value a general payoff function, so we start with risk neutral density Q, but we end up with using only these the plain vanilla options, put and call options P and C. So it means that we do not even need to extract the risk neutral density from options. We could just directly use the put and call options, and in order to value a general payoff function. And this formula from Kalman, it's highly used in practice, and there are many different applications. And for instance, one of the I think well-known example would be the VIX index. So if you were wondering how the VIX index is derived, you can apply this formula to log ST, and you will end up with VIX index formula. I think one of the most known fear indices of the stock markets. You can also derive some corridor implied volatility, and you can also extract some different risk neutral moments. There are also papers looking at the third and fourth moments extracted from the options. And there's a paper also by Viktor Todorov who applies this formula to extract the characteristic function. And that's what we actually are also going to do now here. So the characteristic function phi is conditional expectation. So we will look at the characteristic function of log returns. So of log ft over f capital T over ft. F here stands for future prices, but you can think of them as just stock prices st. So, and we're interested in this characteristic function of these log returns. And of course, the characteristic functions, they have very nice properties. But what will be important for us that they basically define a whole distribution of a random variable. So there's a correspondence between the distribution PDF function, if it exists, for a random variable and characteristic function. And here, so we will apply this payoff spanning formula for this function j of this form. So we take the second derivative of that, and then we can find this basically that this characteristic function of log returns can be written in terms of these option prices. In a sense, we are constructing a portfolio of option prices, and here in position in bond prices, such that we, in some sense, replicate the payoff of the characteristic function. Okay, so in a sense, this characteristic function here, it's a portfolio of option prices. Yes, as I said. But what is important?
Evgenii, so why is this? What's the benefit of using characteristic function?
So, benefit of so in the option pricing literature and in the continuous time asset pricing literature, also very often there is no closed form for the density function for the CDF function for the models, but the characteristic function often exists in a closed form or semi-closed form, as I'll show you in the next slides. That's why people very often use characteristic function, because it's instead of PDFs, for instance, which are not, they don't exist in a closed form. And then you use it to price options, for instance. Yes. But what is important here that this formula is exact, and it is completely model independent. So I do not assume any parametric assumptions, any dynamics on these prices of f capital T, or ST if you want. Yes, but one kind of small issue here that this characteristic function, in practice, we do not, so it requires a continuum of strides k. So k has to range from 0 to infinity. And in practice, we do not have this luxury. We have only discrete set of strike prices at each day, but nevertheless, we can still approximate this well using some interpolation extrapolation schemes, given this discretely observed strike from K1 to Kn. So I will be denoting by phi hat this approximation. Okay, so on the other hand, this there is a large stream of literature who deals with the so-called, who considers parametric option pricing models, and in particular a class which is called an affine jump diffusion class of models. So, which is in general written in this form. So it has a, as usual, diffusive and jump component term. But one of the defining properties of this affine jump diffusion class is that its characteristic function of the state vector xt is given in this exponential affine form. So xt here is a state vector, so it includes all the factors that drives the dynamics of the asset. So in the Heston model, it will always include a log of the underlying asset or its future prices, log of t or log of t, and stochastic volatility, for instance, as in the Heston model. So yes, and the characteristic function, joint characteristic function of this state vector xt is given in the exponential affine form for this class. This is the defining property of this class. And here the coefficients alphas and betas, they are parameter dependent, and they are solution to some general ODE Riccati system. And but which can be solved, and in some cases they are known in closed form analytically. And but in order to get the marginal characteristic function for log returns only, what we can do is simply to plug in the argument vector u1 of this form, where we have only one element and the 0 other elements, then we'll get a marginal characteristic function. So this class is very, very large and includes most of the option pricing models that is available out there. Most likely they will belong to this class. So, and there are this list of few of them. But of course, there are models also from that does not belong to this class. Okay, so we have one way to find the characteristic function, which is completely model independent, and we do not assume any parametric assumptions here. And the other approach is to use a parametric assumptions on the dynamics of the model, and then we can also obtain this conditional characteristic function. It means that we can align these two, and in fact, if we take the log of this model-implied or option-implied model-free characteristic function, then this log of this characteristic function will be just a linear function of this state vector xt. And of course, in practice, we have some observation errors, and also there's approximation errors. So we will be working with this equation 4. But what is important here that this is a linear relation in the state vector, which is quite rare for option pricing theory, for option pricing estimations. But also, it is actually a continuum of linear relations, because here u is an argument of the characteristic function, and it can be any real number.
But Evgenii, sorry,
yes.
This implies some assumptions on the characteristic functions. This linear representation in X, and then the question becomes, what is the implied restrictions on the densities?
So we impose assumptions on the parametric models. So we assume that the model is a affine jump diffusion class, and it means that this characteristic function has this exponential affine form. But nice property of the characteristic function that they always exist. And in this case, they exist in semi-closed form.
Yeah, that goes back to my question of what's the point of using characteristic function as opposed to densities, assuming that they exist. So your answer was that you're going to get some closed form expression.
Yes. No, but the problem is that very often, except Black-Scholes model, there, I don't know other option pricing model that have the closed form density functions. Okay, there are some, but there are just very, very few, I think. But majority of the option pricing models, they do not have density in the closed form. And so what you can do, of course, if you have but they do have semi-closed form characteristic functions. And of course, you can apply some Fourier inversions to get the density functions back, but that also will be costly because you will have to integrate over some domain. Oh, I'm not fully. I don't fully understand.
My question is, what restrictions are implied by this assumption on the characteristic function?
You mean this one? This assumption here?
Yes. How strict is this?
It is strict to some sense, but it is, as I said, there are like most of the option pricing models assume that the class belongs to this affine jump diffusion class, and it means that they will have this form of the characteristic functions. Yes.
It is different from exponential class in statistics. That is usually defined for densities, right? Not for characteristic functions.
Yes, I think exponential distributions are, yes, they're defined.
No. Yeah, it's exponential class of some objects.
Yeah, not exponential distribution, but yeah, exponential class, they are defined in terms of the densities. But here, this class is defined in terms of the characteristic function. Yeah, maybe I should say. So there are different ways also to define this class of affine jump diffusion models. And another way, so one way is assume this exponential affine form of the characteristic function, but another form is to say that this drift and diffusive term and the intensity process, they are all affine function of the state vector xt. So for instance, you very often mu xt will be of the form a plus bxt, something like that.
It's interesting.
Of course, yes.
It's interesting if this class includes stable distributions. Stable distributions are defined in terms of characteristic functions. So we have infinite variances. These are extensions of normal distribution. But for them, the imaginary unit is there in the definition I. Although in the symmetric case, they are real valued. Are these characteristic functions real valued or complex objects?
No, the characteristic functions are in general complex valued functions.
So there is I somewhere here, right?
Sorry?
I, imaginary unit, is it here?
So yes,
in the definition?
Here. Yes,
here.
it is,
Okay,
of course.
yeah. But on the right, on the right, I do not see it. Is it in beta?
Yes, because yes, I should have maybe. Yeah. So it is in the ODE system. It is in the boundary conditions for ODE system.
Thank you.
So, but in general, these alpha and betas, they are also complex valued functions.
Yes.
Yes. Yes, maybe let me also go here. This some properties of the characteristic functions for those who are interested. But yeah, of course, moment generative function and characteristic function are interlinked to each other. But the nice property of the characteristic function, it is always bounded, and it always exists, regardless of the moments. So you might not have moment generating function, or it can be degenerate, but the characteristic function will always exist, and that's a nice property, and that will be also useful here in this case.
Evgeny, on a related note, perhaps you know Jan Martin has a sequence of papers on asset pricing using moment generating functions and the implied cumulants. Cumulants are defined in terms of moment generating functions, but it's very restrictive assumption existence of MGF. It would be interesting to conduct the analysis in his framework using characteristic functions, perhaps. I posted some of the papers.
Okay, thank you. I will. I probably haven't seen this paper, but I will have a look at that. Thank you. And so yes, what is U1? U1 is defined here as a vector of this form where we have only the first element is U and the other elements are 0. So this is of the same dimension n dimension as the state vector xt. Okay, this is we will use this form to get the marginal characteristic function, because this is a general, this is joint characteristic function for the state vector, but we'll be interested only in the marginal for log returns. Okay, so under this parametric assumption, under this affine jump diffusion class, yeah, we will have this linear relation. As I said, this is a continuum of linear relation, but in fact, this is actually what we have is a continuum set of complex valued linear relations, because all of these objects are complex valued except the state vector xt. And so if xt is observable, then we can simply find these theta's parameters by simply solving some sort of a continuum version of ordinary least square, and in a complex domain. And but if xt is will contain some unobserved latent states, and then what we will do is use the Kalman type of filtering technique. So, and this equation will serve us as the measurement equation for the state space representation. So, but in general, what we also will need for that, the so-called state updating equation or transition equation, state transition equation. So, and here I partition xt into the observed part and latent states xt, denoted by small xt. And it can be shown that if the model, this affine, belongs to this class of affine jump diffusion models, then, and under the physical measure as well, then this conditional mean of this latent state and conditional variance of this state are also going to be a affine function in xt. So, and which allows me to write it down in this general form. And it means that what we will have is linear state updating equation for this unobserved state process xt. And we can write it as equation for with some errors eta t. Okay, and again, this variance of these errors are going to be a affine function of this xt. But of course, it won't be Gaussian or any other. So we do not impose these distribution assumptions on these ones. Okay, so going back to this Heston model that I showed at the beginning. So, but now it's written for log prices, log future prices. Then we have measurement equation given in terms of this characteristic function, a log of this characteristic function, and it is going to be linear in the volatility vt. And the state updating equation we will write down in terms of this conditional mean and variance of this square root process Vt. Okay, and we will have this equation here. Okay, so this is just a small note. So I'm using here different kappa here and kappa here are different because they possibly might be different under the physical and risk neutral probability measure. Then we will have the so-called diffusive volatility risk premia. But so far I will set them to be equal under both measures. So there are some econometrics challenges. So first of all, we are working with continuous functions rather than discrete set of observations. But because they are continuous, we can well discretize them. And instead of using a continuum of values u, we will restrict ourselves to a finite set of these arguments u that would belong to some set capital U. This also relation, again, complex valid measurement equation, but the state vector as xt is really valid. So that allows us basically just simply to stack the real and imaginary parts into vectors. So if we have an object, complex valued object, we'll be working with its stacked version where we stack simply real and imaginary parts. And what we also will be stacking here basically all different arguments of this characteristic function. So from this set, real and imaginary parts, as I said, and also if we have at the same day several maturities of an option, we also will stack them into one vector, which we will denote by y. It will be a quite large vector of dimension p, which is 2 times q times k, and we will also stack all the other coefficients parameters, alpha, betas, and epsilon. So in the end, what we'll get is this linear measurement equation given by this equation 6. And we will also have the state updation equation given by equation 7 here. Yeah, and this form is general. So it, in a sense that we can, that any AGD model, affine jump diffusion model, can be written in terms of this state space representation, which is, again, is a linear state space representation, which allows us to use some Kalman type of filtering techniques and basically filter out these latent states, XTs.
So,
okay,
Evgeny, this would mean some sort of restrictions again on the types of distributions. For Kalman, the standard is the normality, right, on things like ease.
Yes, yes. So for the Kalman filter, indeed the Kalman filter is derived under the Gaussian assumptions. But if the assumption is the errors are not Gaussian, we can still employ the quasi-maximum likelihood estimation to find the parameters, and the filter will be optimal in terms of the mean squared errors in this case, rather than just being optimal in a general distribution sense. And yeah, but very often the Gaussian assumptions are violated in practice for many other state-based models, and quasi-maximum likelihood very often is used there. Yes, but another kind of issue here that the dimensionality of this state vector y is very large. So it's much larger than this dimensionality of the state of the unobserved latent state xt. And also the information. So if we use the dense set of this argument, then the information in the cross section will be very much alike. So if we take a characteristic function of u and for characteristic function of u plus epsilon, they will be very much similar, and which makes this covariance matrix H most likely non-invertible. So to deal with these problems, what we will use is the so-called collapse Kalman filtering technique, or Kalman filter collapse by transformation proposed by Barker and Kopman. And the idea is that we will transform a high-dimensional vector into a pair of two vectors yt plus and yt star and yt plus, such that only the yt star vector will be a function of the latent state xt, but the yt plus will not depend on xt, and such that this the errors et star and et plus will be uncorrelated. Okay. In fact, this is possible to do with these projection matrices, and at star is just a general least square projection matrix in this case. And here, in fact, we show that this is possible to do even with matches, covariance matches HT that are near singular. So we will use pseudo inversions here. So this transformation, basically, as I said, allows for us to work now with, instead of a high-dimensional state vector yt with yt star, which of the same dimension as the state vector xt. And that makes computational much more feasible, because we will need to invert large dimensional matrices in this Kalman filtering procedure. Okay, and the last note for the estimation that we will also need the covariance matrix H. And of course, it is not going to be a diagonal, because we simply stacked real and imaginary parts. They are not going to be diagonal. And it's most likely will be also, as I said, will not have full rank as well. But we still can use pseudo inverse of this matrix H. So if we assume that errors are independent across different maturities for each day, so then the covariance matrix will have this block diagonal form, and each block will be given by this of this form, where gamma and C are covariance and pseudo covariance matrices, because we're working with complex valued errors in this case. Yes, and finally we impose some additional errors on the observation error scheme, and we derive some closed form for this parametric covariance matrix. Okay, so finally, to wrap up this estimation procedure, we'll look as following. So we first will need to obtain a model-free option-implied characteristic functions for each day and for each maturity in a day. Then we will, assume some affine jump-diffusion class of models, we will have a model-dependent characteristic function. And we can then form a linear measurement relation, as I showed before. And in general, we formulate this state space representation for this affine jump-diffusion model. And then we will use the collapsed Kalman filtering to estimate the model parameters and filter out the latent states. Yes, so this is some Monte Carlo experiment. So we considered many different parametric models, but this one, I will present this one because it matches with empirical application. So we have a bit richer model, parametric option pricing models. So we have also include now jumps, positive and negative jumps into the returns. And we also include jumps in volatility. So yes, we will model here as Poisson jump processes for positive and negative jumps, and also with jump intensities lambda t plus and lambda t minus. And lambda t minus is basically also a time varying jump intensity of negative jumps in this case. And as you can see, the volatility also is allowed to jump together with negative jumps in the returns. And all of the jump size distributions are in this case assumed to be exponential form, or from exponential distribution. So so this is simulation setting, and we also add some errors into the option prices, but in terms of Black-Scholes implied volatilities. So yes, we assume that option prices observed with some errors. So this is Monte Carlo results of this Monte Carlo experiment for different ranges of this argument use, and you see that for most of the parameters, especially for the range with larger arguments of the characteristic function, we have a very nice finite properties of most of the parameter estimates, except maybe some related to positive jump intensities. Yeah, so, and we will apply this basically the same model in the empirical application that I just wanted to also briefly show you. So we use S&P index option from CBRE that covers this almost 3 years, almost 1,000 trading days, including the coronavirus outbreak. So at each day, we keep options with 6 different time to maturities with less than 22 months of maturities. And we also apply some delta data filters and extrapolation, interpolation techniques. And so in this here in this table, you can see these parameter estimates for the same model applied to this data. And so most of the parameters also are consistent with what is found in the literature. And we see here that, for instance, the positive jumps, the mean of the positive jumps is around 1%, and mean of negative jumps is around 4.5%. There's also large jump sizes, large mean of jump sizes and volatility, but this is also most likely due to the case that these jump sizes absorb some self-excitation effect also in these dynamics. Of course, given these parameter estimates, because we are exploit this Kalman filtering technique, what we can do, we basically can filter out the latent states, which in this case also was this volatility process. So, and this is a filtered volatility, and you can see that it very much resembles the dynamics of, for instance, of the VIX index, and you can see that it largely jumps up during the COVID outbreak at the beginning in spring of 2020. And
Evgenii, can we take a look into the previous table, the one before on that previous slide, the one before?
Okay.
Yeah, you mentioned that the estimates are good. That is, the truth is close to the mean, right? For all the parameters, and you mentioned except some of them, except delta 1, I suppose, and delta 0.
So yeah, some parameters of concern are these delta 0 plus and eta plus, because it seems like there is not so much information to well identify them both.
And what are these parameters exactly? What do
so
they
these parameters, so delta 0 plus, this is intensity, constant intensity for positive jumps, and eta plus, it's a mean of these jump size, of positive jump sizes.
Thank you.
Yeah, but we're also considering now, so this is ongoing work, and we're considering also different other parametric models to see how they perform as well. Okay, and yeah, so this is the filter volatility, and as the last part, what I wanted to show, so is adding some external information into the same model. And and the motivation comes from the fact that a market crash in 2020, the source of this kind of market fears is known, which is namely the COVID-19 pandemic. And we were thinking, well, okay, then maybe we can embed the fears in terms of the COVID into this same model and see how it affected the volatility and the likelihood of jumps in the stock market. So in particular, what we do, we embed is the reproduction number, R0, into the same dynamics that I showed you before. So we don't want to assume any prior knowledge of this dynamic. So we do not want to impose any parametric dynamics on the reproduction number. And that's why we think that we assume that it is affect in a constant way throughout the lifetime of an option, but of course, in a sense that this process is deterministic. So, and this assumption will lead to some negligible, what we think, errors, because if this process will be persistent, and this assumption will be reasonable to assume for persistent processes. And this is in a similar way how interest rates or dividend yields are treated in option pricing. So they are often assumed to be deterministic. Okay, so in particular, what we'll do, we say, okay, let's now add to the jump intensities, to positive and negative jump intensities, these reproduction numbers with these loadings gamma plus and gamma minus. And we also add this reproduction number with some coefficients Q, proportionality coefficient, into the diffusive term of this model. And yeah, so as I said, this RT will affect only the level of these intensities at a particular time t. So we do not have here an equation, dynamic equation for the reproduction number RT here. So only these two equations. And and this is we also ran some Monte Carlo for this model, of course, and yes, we show that these parameters can be also well identified in a finite setting, even assuming basically misspecified, running misspecified model for the reproduction numbers. So in this table, for this model with external factors, and in this case, parameters of interest are these ones. And we see that the gamma plus is very insignificant and close to zero. But gamma minus, so this is a loading for negative jumps, is actually positive and significantly different from zero. And also the diffusive term is also very close to zero. It means that the production number of the COVID pandemic, they drove up. We're noting that this is one of the source of the jump intensity of negative jump intensities in the stock market. So, and finally, this is a plot of these intensities extracted from this model, decomposed into this part, with basically we have only delta 1 with volatility and delta 1 with volatility and this reproduction number, and we see that this gap basically can be explained in this case by the reproduction number of COVID-19 pandemic. Okay, I think that's what I wanted to share. So in this paper, we developed a new state filtering and parameter estimation procedure for a general affine jump-diffusion class of option pricing models. This procedure is based on the linear relation between log of the option-implied characteristic function and state vector that follows this affine jump-diffusion assumption. And under this assumption, the linearity of the measurement equation and state updating equations allows us to use the Kalman type of filtering technique, and that makes the computation estimation very fast and easy to implement, which is very untypical for option pricing literature. And also at the same time, because it is based on the characteristic function, we use very rich set of probabilistic information from the option prices. And so our Monte Carlo results show very reasonable finite sample performance of the for these models, and we're also and we're currently also working now on this application for S&P 500 index options and during the pandemic time as well. Okay, thank you for your attention. Yeah, if you have any questions.
Thanks, Evgeny. Any questions for the speaker?
Since one works with logarithm of characteristic functions, it's
this is
exactly
essentially a cumulant, if you want.
Yeah. I was going to say that cumulants are derivatives of logarithm of characteristic functions. So it may be interesting then, going back to the previous comment, perhaps use the results in, maybe the approaches are useful in asset pricing. Instead of moment generating function, use characteristic function, and then that will always exist. A lot of all utilities will be allowed except exponential ones, say that Jan Martin considers or more, and will be a much more general analysis. I was still thinking about stable distributions. So stable distributions, there is a formula, standard formula for characteristic function there on the right of this article. So that involves the argument to power alpha, where alpha is the tail index and also index of stability. I wonder if then, since you have linear x argument linearly entering characteristic function, if you look into its formula, I wonder if stable densities are just ruled out in principle. Or can u be to some power here? Can alpha and beta be such? Can beta be such that u is raised to some power alpha?
But for this stable distribution,
so that stable characteristic function involves the argument t, or in our case, u to some power alpha. If beta can be such that these power functions are allowed, then stable distributions are covered, as I understand.
Yes, I think they should be included, but I don't see the. So in this case, it is a conditional characteristic function, but phi is.
Perhaps it may be interesting to see
but I think it should. Yes.
Perhaps it would be interesting to see if stable distributions are covered, and then many heavy-tailed distributions are allowed to them.
Yes, I think it should be covered here.
And you mentioned solutions to ODE system. Which system is that, Evgeny? Definitions of beta, say.
So I don't have it here, but in these slides. But this is a general Riccati ODE system of Riccati formula. But here this class allows for jump components as well, and you can make the returns to be heavy-tailed by assuming some jump sizes to have some heavy-tailedness as well.
Is it perhaps not heavy-tailedness, but crisis will be allowed, that is crashes?
Yes.
So there are two ways to model crisis, either using heavy tails or a jump component, which is kind of analog of discrete.
Yes.
Discrete jump. Yeah, thank you.
Thank you.
Any other questions? Well, if there are no other questions, I'd like to thank Evgenii for a very nice talk. Send him this virtual applause. Thank everybody
Thank you very much for your questions and for listening.
for being here.